Okay, in our last video, we established datum A. We made sure that the surface finish of datum A was better than the 125 surface finish. We did that with a comparison chart. Today, we are going to talk about datum D, this side of the part. Now, you may get confused. Don't get confused with datum B, which is right here. That datum B is the overall width of the part. Now, also, datum D needs to be perpendicular to datum A within 2/1000 of an inch. When we're all done with that, we want to make sure that we deburr this part. Up here there's a note that says break all sharp edges 15 thousandths max, and we'll discuss that later in this video as well. So on our first step, we took the part, put it in the vise, up high on parallels, and we machined it off. And we created datum A. Now on the second step, we're going to take this part again, we're going to throw it up in the vise, this being our fixed jaw. We're going to take a parallel and just kind of throw it up underneath this. We're going to kind of lay it down, and we're going to take this part, put it in the vise, this with datum A right here on the back side, right up against this vise jaw. We're going to take a round rod and push it there so that we maintain the squareness that's attached to this jaw. Now, we can't use a lot of pressure on this vise, and I want to show you why. If you take the screw on a vise jaw, it's about a 1" 8 thread. 1" 8. So in order to figure out the mechanical advantage of that, we'll take the circumference of the screw, and really it should be done with the pitch diameter, but we're just looking at for a ballpark figure right now. So the circumference is pi d, which in this case is 3.14 times 1, which gives us 3.14, and we want to multiply it by the length. So 3.14 times 8 threads per inch, and that means in 1 inch travel, we're going to travel 25 inches. So for 1 inch travel on the vise, on the screw, we're actually increasing that 25 times. Now, if you take the length of the handle of the vise jaw, which is 9 inches, 9 times 25, that gives us 225. 225 times is what the handle on the vise multiplies the force by. So if we put 10 pounds of force on that vise handle, and multiply that by 225, you can see that 2,250 pounds of force. So we can really put a lot of force against that back jaw. Here, just 10 pounds of force on that vise handle is going to equate to a ton of force back on the vise. Okay? So let's set this up and get ready to mill this. Okay, so now you can see how we've got this part set up. We're going to take this parallel out from underneath it because it doesn't really do us any good. We want to take as much influence out of that part as possible. So we're going to take this out of here, just lightly snugging on the vise. So I've put an indicator against the back jaw of this vise, and I've lightly snugged up on this vise, but I want you to see what happens when I start to really crank on this vise. Notice what's happening to that indicator. The back of this jaw is actually deflecting, moving away. So when we tighten this up, we really want to make sure that we're not tightening up so much on this thing that we're deflecting this vise jaw. Now, it's got to be snug enough to hold this part, but there's a lot of surface area involved, so we really don't have to worry that much about the part moving as long as we're taking a light cut. And that's all we're doing at this point. We're just trying to square up those two sides. So now we're ready to start cutting this. You can choose any method that you want to make your cut. I'm going to use the 3/4 inch end mill. We'll bring the cutter down to touch the workpiece. Back it off the part. I'm going to crank up about 6-7 thousandths. Lock my table in the up position. Lock my cross slide. Turn on the spindle and cut the part. Now you can use power feed with this if you like, and I want you to see on this digital readout that little F up here in the top where it says 4.3, that's 4.3 inches a minute that this machine is moving at right now. So now we're going to deburr this part, but we have to be careful about this corner. That corner still needs to remain fairly sharp. When we talk about that 15 thousandths maximum break, a true deburred surface comes right up to its corner and we end up with a little scraggly edge on the end of it. A true deburred surface takes that off. Now, it says 15 thousandths maximum break, which means that this corner here can be actually broken. So this area in here ends up being 0.015 or less. And we can check that with a radius gauge. If you take a 64th radius gauge and hold it up here against this corner and it rocks, it's okay, it's good. If it sits flush in that corner, it's not okay. Okay, so we're going to check the corner of this part using a radius gauge. And you notice, as I hold it up in here, you notice that there's a little rock to it. So, in this case, that's okay. Now let's check it for squareness. So, to check this thing for square, we've taken the A side and mounted that up against this magnetic V block. The V block is guaranteed to be square. We're going to take our indicator and drop our indicator down on top of the part and move it from front to back. In this case, we see 1/1000th of an inch. We aren't so much concerned about side to side, but we are from front to back. And those are the only two surfaces we're worried about right now. So right now we have surface A and surface B.